Hey everyone, we are looking at the topic of static equilibrium, which is when an object isn't moving, when things like forces are balanced. We first learned about this earlier on. Now we're going back and including the new topics of rotation and what that means for these kinds of problems. So first, our definition of static equilibrium. If something is in static equilibrium, that means it's not experiencing any translation, remember that's motion from one spot to another, nor is it experiencing any rotation, it pivoting along some axes over some amount of time. We saw this before when we had like a block sitting on the table. We knew that we could add up all the forces, and if the object isn't moving over time, they must add up to zero. We're going back to that, but we're going to look at some more complicated objects. And by that I mean objects that have the ability to potentially rotate over some axes. We're going to focus on kind of the classic teeter-totter example. Here, this green plank of wood is designed to possibly rotate. All right, maybe this dog is going to make it start rotating, but we'll start with when it's not rotating, when the net force is zero, in both the x and y direction, and the net torque is zero. Because remember, if something's not rotating, it can't have any net torque. Before we start analyzing these problems, we have to go back to center of mass, because understanding what that means is going to have a large effect on how we approach these problems. All right, when we first introduced center of mass, it was kind of like the average of where the masses are located. Okay, where the mass of one object or a system of objects is. And while that's still true, right now the easiest way to think of center of mass is this, the balance point. If you held an object at its center of mass, if you kind of balanced it on your finger, all right, well, it would in fact balance at that point. Well, if you have an object like this blue bar here, if the mass is evenly distributed, think of the teeter-totter. I would want to put our hinge, our balance point, right here. And it would, in fact, balance. All right, I have just as much mass and therefore just as much weight over here as I do over here. So those two torques, as we now know, would cancel themselves out. But even if you don't recognize that yet, it's just where the object would balance. Imagine I had something that wasn't symmetric. So I have a lot of mass over here. Something over here is, or the object over here is very light. I would have to have that hinge way closer to this side to have it be balanced. Again, the average location of the mass, and therefore the weight, would be here in this case, and here in this case. And if I put a hinge underneath where that center of mass is, the object would balance. For the most part, we're going to look at these examples. All right, we're going to look at objects that have a uniform distribution, and therefore the center of mass is going to be fairly straightforward. It'll be at the geometric center. Okay. Well, to approach static equilibrium problems, we had a set of strategies, and I have, for the most part, the same strategy with a couple of key exceptions. When we're trying to look at equilibrium, when we want to add up all the forces and now all the torques, we always want to start with a free body diagram. We used to draw free body diagrams as just a dot, but to be honest, we don't want to do that anymore. We want to actually sketch the object. So if you think of the teeter-totter or those bars I had on the last slide, we want to now actually sketch the object because now it depends where those forces are acting. If the force is where the center of mass is, if it's far to the left, far to the right, that's going to determine the torques that are acting on it. Because remember, torque is based on the force and how far away that force is. So it's important to recognize where those forces are. So we're kind of going from our regular dot to an outline of the object so we can see exactly where those forces are. Force 1, force 2, force 3. You get the idea. Number 2, we want to pick an axis, a hinge that's convenient. For the teeter-totter, the balance beam, pick where either the hinge itself is located or where the center of mass is. So we often want to do this where center of mass is. where COM is, especially for the teeter-totter. We'll see some examples in the near future where this might not always be the best case. Okay, I give you a hint here, which we'll look at later on, and a little bit today, I guess. If you have an unknown force, if you pick a hinge at that location, there's not going to be a torque. If I have my hinge as right here, notice F2 would not produce a torque because there's no R, no distance away. Okay, so we'll want to pick an axis, a spot where it's rotating about. Number 3, are positives and negatives. I used to do this all the time, right? Up is positive, to the right is positive. Now I like to draw this. These are all my positive directions, up, right, and counterclockwise. That is the convention. Once you know where your hinge is, because that's going to tell you where to measure R from, once you have your positives and negative directions known, you can write out our equations, sum of the torques, sum of the forces. Usually the trick is for these problems, start with the sum of the torque. That's usually your best bet. Okay? More often, if you start with these ones, you're not going to have enough info. You'll have to go back to this one anyway, and then try and solve. So let's look at a quick example. I have a classic teeter-totter, and in this example, let's say this teeter-totter is balanced, so it's not rotating. Let's make that clear. So in this example, it's not rotating. That means it's an example of static equilibrium. In this, I have the teeter point, the hinge right here. I have a mass located here. I'll call that mass 1. Let me get a better color pen. Mass 1. I'll call this one mass 2. Well, let's do our classic setup and follow our strategy. So step 1, I've kind of already labeled it right here. Let's make a free body diagram. I'm not going to draw a dot. I'm going to actually draw this beam. I already put it in. Let's label the forces that are acting on it. Well, this M1 is exerting a weight, and it's right over here, M1G. This mass 2 is exerting a weight, M2G. I don't know for sure which one is bigger or smaller. I might be able to make an educated guess based on the fact that it's balanced. Okay, there's the weight of this plank itself. Okay, if this bar has some mass, you might have to consider that. And the mass of the bar, let's call that M bar. That always acts in the center. Some problems, they'll say to ignore the mass of the plank. Ignore plank's mass. In which case, you'll do just that. If something is really light compared to the masses on the two ends, you could ignore it. But in this case, let's just draw it in for the sake of having it. Are there any other forces? There is. If this is a teeter-totter, there must be some normal force from that teeter-totter itself. So right there. Okay, it must be applying some upward force, which we normally call the normal force. Okay, those are all the forces acting on it. Step 2, let me change color pens. For step 2, I want to make sure I know where my hinge is. Well, I'm going to have the hinge where it's actually physically drawn. That's nice and easy. So there is my hinge. Step 3, I'm going to change pens again to blue. Let's make our clear and obvious, and I'm going to follow the convention. Up is positive. Oh gosh, that wasn't drawn very well. To the right is positive, counterclockwise is positive. All right. Step 4, let's write the sum of the forces and the sum of the torques. Let's start with the sum of the torques. First, this mass 1 is exerting a torque. Torque from 1. That torque is going to make it go counterclockwise, so I'll have that as positive. This torque from the bar would make it rotate this way. That's clockwise, that's minus. So minus the torque from the weight of the bar itself. Okay, well, there's also this. There's the torque from M2. And that would also make it rotate clockwise, which I call negative. All right, any other torques? Well, you might think maybe we have to add the torque from that normal force. And okay, fine, why not? Equals 0. Well, let's add these up. Torque 1, that's m1g. How far away? Remember, torque equals RF perpendicular, excuse me. That's L1. Minus the torque of the bar. That's the mass of the bar times g. To be honest, I don't really know this distance here. I didn't label it in the problem. Let's call it r. Minus the torque from this weight. That's m2g, that's the force, times the length is L2. Plus the normal force. What's the distance from the hinge? Oh, look at this. The normal force is acting where the hinge is. So that means it's not producing a torque. This here is 0. R is nothing for the case of this normal force. Convenient, that goes away. That's why I said in the previous slide, sometimes it's nice to pick a hinge where you have an unknown force, because there's not going to be a torque at that spot. And then obviously, based on the info in the problem, you might be able to solve for this. Mass of the bar times g times r minus m2g L2. If it's not rotating, it equals 0. And then you might continue in the problem. Maybe you would look at the sum of the forces. Well, the sum of the forces in the x direction, that's 0. Sum of the forces in the y direction, you can do this. That would be m1g minus m2g plus the normal force minus the mass of the bar times g. That all adds up to 0. Okay. These are the approaches that we want to take over the next couple of days. All right, we'll be getting a lot of practice on these. Thanks a lot. There'll be another video doing an example in the near future. Thanks for watching.